So let me first share today's lecture slide, and after that we can start today's lecture. Just a moment.
Sir, please record the lecture.
Yes, that I'll do. Okay. I'll record it and I'll also share it. Okay. Just a moment.
Yes.
So just now I have shared my laptop screen, and I hope it is visible. Is it visible?
Yes, sir.
The lecture note, is it visible?
Yes, sir.
Visible.
Yes, sir.
Okay, so shall we start now? Okay. In the last class, we did discuss about simple harmonic oscillator. In fact, we began by giving a number of examples where we can see oscillations, and then we said we have harmonic oscillation if you have harmonic approximation, and then we said that we could have three different type of harmonic oscillator: simple, damped, and forced. So last class we did discuss extensively about simple harmonic oscillator by considering a mechanical oscillator, which is spring mass oscillator system, and the pendulum kind of thing.
This call is now being recorded.
In today's lecture, we will be discussing about damped harmonic oscillation, and a harmonic oscillator with a damping force is known as damped harmonic oscillator. If you remember from the last lecture, we said that there are two additional force one can apply. In fact, will not apply. We'll find two more forces are associated.
Resistive force, and external force.
Yes, yes. So everybody, please go to mute mode. So unless I ask you to unmute, okay? Because we are recording, so so please, everybody should be in mute mode. So if we have resistive force, right? Then we have damped harmonic oscillator. Okay, and frictional force. And you have viscous force, even drag force. So they are examples of resistive force, and they can act on an oscillator, and the damping can occur, right? And in general we can say the resistive force or damping force. And the damping force, right? So how it relates with parameters or variable that associate with the oscillator. So as you know, the displacement, velocity, acceleration, and so on, they are associated with an oscillator. So the damping force, which is normally represented by F subscript D, is directly proportional to the velocity. Okay, whether you have frictional force, viscous force, or drag force. So that case, you can intuitively, conclude that the damping force is directly proportional to velocity. So, for example, if you try to move or swim faster, let's say in a swimming pool, what will happen? Then you will find more, more resistive force, right? So in that sense, the damping force is directly proportional to velocity, and that it is an approximation, like harmonic approximation. We could have in a higher order term, but we can again neglect because this approximation is good for low velocity, like harmonic approximation, where we have the restoring force is directly proportional to displacement, and therefore we have famous Hooke's law. So the damping force is directly proportional to velocity. As I said, you can intuitively, conclude that if the velocity will increase, the damping force will also increase, but it will, act the opposite direction of the velocity. So therefore, we have a negative sign here. Okay. So now we know that how the damping force relates with the velocity, which is one of the parameters that are associated with an oscillator. Okay. So again, we'll progress similar way that we had already done for simple harmonic oscillator. By the way, I am audible, right? You can hear me.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you. So as I said in the last class, that we have to convert to a mathematical statement, and then we'll try to find out a solution, right? And the solution could be your displacement, velocity, acceleration, and so on. So here is the schematic diagram. So again, we'll work with horizontal, spring mass oscillator system. You can have vertical spring mass oscillator system that I'll put in the assignment again. But the method will remain same. So here x naught is the mean position, resting position. As I have said, in the last class, whenever you are using some notation or symbol, you have to explicitly mention them. Otherwise, they do not make any sense. So x naught is the equilibrium or resting mean position. M is the mass of the oscillator. K is the spring constant associated with the oscillator. And again, we just try to disturb from its mean position in order to get oscillation. So let's say for an instant of time or a given instant of time t, it's a random, right? When I say instant of time, it is known in any time, so it's a random. At a given instant of time t, let's the oscillator is found here, x of t. Okay, here. So now what will happen? We have a spring force where it acts in left direction, and then the damping force, because the oscillators are moving in the right direction, so damping force will act in the left direction. And assuming the oscillator is still continuing to move along right hand direction. So these are the forces that are associated with the oscillator at an instant of time t. So that I have defined here. Okay. So A is the acceleration at that instant of time. So now what are the forces? This is simply from Newton's law that we have already seen in the last lecture. This we have already seen. And then the damping force is directly proportional to velocity, and we have a proportional constant B, and B is known as the damping constant. So we know the mathematical expression for all forces associated with the oscillator. So at given time t, so these forces will be balanced. Okay, so therefore we have this equation, and we have finally this equation 1. Again, it's a second order ordinary differential equation. Okay, with gamma, which is v over 2m. Since v is the damping constant, then we can tell it's a damping coefficient, or rename it's a damping coefficient. And omega naught, we have already seen, this is the frequency associated with the oscillator. Okay, and since the oscillator, when it is free from other kind of forces, for example damping force, external applied force, so that would be the natural frequency of the oscillator. Okay, because there are no forces acting on the oscillator, hence it's called natural frequency of the oscillator. Is this clear so far?
Yes, sir.
Yes, sir.
Yes or no? Okay, so let's progress. Let's move on. So the solution, what would be the solution? We have to start the initial case solution. X of t equal to a e to the power alpha t, where a alpha to unknown constant, and then we have this equation. Then we have this quadratic equation. Okay, either the term sitting in the square bracket will be 0, or this will be 0, or both of them will be 0. But this must be 0 because a e to the power alpha t can't be 0, because if it's a 0, then the x of t equal to 0. What does it mean? It's the oscillator is at resting position for in all the time. So therefore, it's a trivial solution in mathematical language. So a e to the power alpha t cannot be 0. Hence the term sitting in the square bracket is 0. And it's a quadratic equation. What is the solution? This one. So we have two solutions, or two alphas. Alpha 1 you can consider the positive sign, whereas the alpha 2 you can consider negative sign, and or vice versa. And the general solution, as I said in the previous class, and all of you might know that we should have a linear combination of these two solutions. A1 into A1 e to the power alpha 1 t plus A2 e to the power alpha t, with A1 and A2 are two unknown constants. Okay, so now what you can see that we can further simplify this equation 2, provided we should know what is this term sitting in the square bracket. That means gamma square minus omega naught square. Is it a negative value? Is it a positive value? Or is it a 0? Or in other sense, is it greater than 0? Is it less than 0? Or is it 0? So we have three different situations. So the first case, when it's a negative quantity, that means gamma square is less than omega naught square. Okay, so that case, that scenario is known as underdamped. I will explain why it's called underdamped. So since gamma square is less than omega naught square, then what we'll find that the term sitting in the square root is a negative quantity. So that I have simplified here. Okay, so we have a negative quantity, then we can have -1 this. So now this term is a positive. So what we can have? The square root of -1, square root of omega naught square minus gamma square. So now this term is a positive quantity. Okay, so now as we know, the square root of -1 equal to I omega naught square minus gamma square. Okay, so we can redefine this square root that omega 1 square equal to, we can have omega naught square minus gamma square. So let's redefine it. So therefore, what we have, this square root of gamma square minus omega naught square is simply plus minus, we can have I omega 1. Okay. So now, if we consider that positive sign, and if you define alpha 1, then alpha 2 will be the negative sign. So alpha 1 is minus gamma plus I omega 1, then alpha 2 equal to minus gamma minus I omega 1. So now this omega, as I said, it's in omega naught square minus gamma square, and it is a positive real number. Why? Because this is a positive, omega naught is a real number, gamma is a real, so therefore it's a positive real number. Okay, so now the general solution will be the linear combination. A1 e to the power minus gamma plus I omega 1 t plus A2 e to the power minus gamma minus I omega 1 t. Simply substituting the value of alpha 1 and alpha 2. And then rearranging the term will end with this equation. Okay. So now this, again, the term sitting inside the square bracket we have already seen. So therefore, we can solve by using the exact procedure that we have done for simple harmonic oscillator. Okay. So I'm writing down the solution. What is the solution? A cosine omega 1. So thus the solution will be A cosine omega 1t plus theta. Okay, and we have this exponential term a e to the power minus gamma t cosine omega naught t plus phi. What is omega 1? Omega 1 is a positive real number whose value is omega naught square gamma square. So it's a positive real number. Okay, and phi is the initial phase of the damped harmonic oscillator. Is it clear so far? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Okay,
Yes,
so
sir.
now the second case. Okay, so when gamma square is greater than omega naught square, so that means the term sitting in the square bracket will be positive. Okay, so now alpha 1 will be minus gamma plus square root of gamma square minus omega naught square. Then alpha 2 will have minus gamma minus square root of gamma square minus omega naught square. Okay, then the question is the alphas, are they complex? No. Why? Because this term gamma square minus omega naught square is positive. The square root of a positive number is a real number, not a complex number. So at least we know that alphas are real. But are they positive real number or negative real number? How will know? Both of them will be the negative real number. How? The question is how. Since gamma square is greater than omega naught square, okay, so then the square root of gamma square minus omega naught square must less than gamma? Yes or no? So therefore, when we either adding or subtracting a less number than the bigger number which has the negative sign, then the final will be a negative quantity. Because the gamma is the bigger number, then the term sitting in the square bracket as a square root is a smaller number. And the gamma is carrying the negative sign. So whether we are adding or subtracting, then it will still remain a negative number. So what we know that both alphas are negative but real. So let me redefine its gamma 1 and gamma 2. Because we know the value of gamma and omega naught, so we can also calculate gamma 1 and gamma 2. So here gamma 1 and gamma 2 are positive real number. Okay, because it carries negative sign. So the alphas are the negatives, whereas gammas are the positive, gamma 1 and gamma 2. So the general solution, what will be the general solution? A1 e to the power minus gamma 1t plus A2 e to the power minus gamma 2t. Again, so this is the simplest solution. Okay. So then the last case, which is trivial, what will happen when gamma square equal to omega naught square? And that situation is called critical damped. That means the terms sitting under the square bracket is 0. So that case, what will be alpha 1? Minus gamma, and alpha 2 equal to minus gamma. So it means alpha is minus gamma. Okay, and since the solution of a quadratic equation, then you can say it's a real and repeated roots. Yeah, we are actually one value, but since we are dealing with a quadratic equation, so therefore we must have two solutions. So therefore, in mathematical language, it's real repeated roots of the second order ordinary differential equation. Those who studies ordinary differential, even if you are 10 plus 2, right? So where you have second order ordinary differential equation or quadratic equation, you could have a repeated roots, right? For example, x square minus 4 equal to 0. Okay, so no, then we'll have a positive negative number. Okay, so you can have a differential equation where when you solve it, you'll have a real and repeated roots. And then if you have a real and repeated roots for a second order ordinary differential equation, then the general solution will be like this: a1 e to the power minus gamma t plus in second term, what you have, a time dependent should be added with the exponential dependent. So this is the standard procedure. Okay, So those who know, no problem. Those who do not know, you should ask your math teacher. So we have a ordinary differential equation second order and real and repeated roots. And why the solution is like this? So they'll answer. Okay. So now, depending on the term sitting in this in the square root, we have three different solutions. Okay. So here, when this gamma square minus omega naught square is a positive number or negative number or zero, we have under damped, over damped, and critical damped. But why they got name like that? So now, before we discuss why they got name like that, so I would like to bring your focus here on the solutions, right? The solution is nothing but the displacement. Now you know the displacement for any cases, critical damped, over damped, or under damped. So therefore you can get the velocity, you can get the acceleration, and therefore you can get the total energy of the oscillator. Okay. So now, so let's plot these solutions. The first case, the under damped case, where gamma square is less than omega naught. What is the solution? A e to the power minus gamma t cosine omega naught t, assuming the initial phase is just 0. And how will plot it? So what we'll see that the plot, okay, must be the superimposition of this exponential decaying function as well as the sinusoidal function, which is cosine function. Okay. So for example, when time t equal to 0, that means the beginning. When t equal to 0, so exponential term will be 0. E to the power minus 0 equal to what? What is the value of e to the power minus 0? So at time t equal to 0. Right? So under damped case, gamma square so this case, what will have? It will be simply A. Why? Because e to the power 0. What is the value of e to the power minus 0? Anybody? It is 1. Okay. And cosine 0 equal to 1. So, so the solution will be A. So hence you can see that it starts from here. A. And when t is very large, when t goes to infinite, what is the solution when t goes to infinite? So e to the power minus infinity is how much? What is the value?
0.
0. So therefore the solution will goes to 0. So hence you can see that as time moves on, so therefore the solution will be 0. It's a decaying solution. And for any other values, what you can have? The superimposition of this two function. Actually you have oscillator function and then it will decay with an exponential. And this will be e to the power minus gamma t. So this dotted dash line. So it will still remain oscillating, but it will decay over time. Okay, and you can get also the time period here. And and then for over damped, so the solution is, what is the solution? We have either e to the power minus gamma 1t or e to the power minus gamma 2t. So again, the exponential decaying function, any one of this red one. And for critical damped, what it will happen that the solution will depend on t e to the power minus gamma t. With the time, as the time increases, so therefore the decaying will be more, because t e to the power minus gamma t will be the dominant term in the solution. So this solution. So this term will dominate over this term. So the nature of the plot of this solution x of t under critical damped will depend on the second part of the solution a to t e to the power minus gamma t. Okay. So when time t equal to 0, this term will be 0. Simply the solution will start a1, because e to the power minus 0 equal to 1. So that. So now here we plot solutions of the displacement of the damped harmonic oscillator with 3 different scenarios: critical damped, over damped, and under damped. So what does they actually indicate? What are the physical significances of this solution or the plot that I am showing you? Anybody can explain? What are the physical significances? What do they actually represent for the real oscillator case? Anybody? Am I audible?
Sir, the amplitude will constantly keep decreasing.
So what it actually tells us that we will have oscillation for underdamped case only. So you see here. So what does it mean? It means, so this is the mean position. So once you pull it, the oscillator, or release it at an amplitude A, it will move back and forth, because minus A means the left side of the oscillator, plus A means the right side of the oscillator, or vice versa. So it means the oscillator will move back and forth around the mean position, and finally it will get settled down. And the other two cases, like over damped and critical damped, so the oscillator will never go the other side of the mean position. So what does it mean? So because they are not moving to negative side of the mean position. For example, if you pull the oscillator at an amplitude at a certain distance, or release it, okay, then the oscillator will slowly will come and get settled down at the mean position. It will never move the left side of the mean position, or vice versa. So the underdamped solution is interesting to study because it shows oscillation, where the overdamped, the critical damped, they are not interesting, since the damping coefficient is such a way that we cross the critical limit where we could not see any oscillation. So therefore it got the name overdamped or critical damped. And since we have parameter in a such a that we have oscillation, so therefore we have underdamped. So everybody understood why they got name like underdamped, overdamped, and critical damped, because we crossed the threshold of the damping where we did not get any oscillation, therefore overdamped or critical damped. And below that critical case where we can observe oscillation, there's the underdamped solution, hence it got underdamped. Okay, so now the next job is to find out the velocity, acceleration, potential energy, kinetic energy that are associated with the damped harmonic oscillator at a given instant of time t, as it perform oscillations. Okay, so now you can use the same method, okay, that we have already done simple harmonic oscillator case, and you can get the velocity, acceleration, and therefore the total energy associated with the damped harmonic oscillator for any one of these cases, namely critical damped, underdamped, and overdamped. And as I said, the underdamped is very interesting because it shows oscillation, whereas the rest two, they do not show any oscillation. Hence, it is essential to calculate the total energy associated with the underdamped part of the oscillator systems. And if you calculate, again you'll find this in the assignment. The assignment I'll upload by today. Okay. So you'll find this problem in your assignment, and then the average total energy will be in this form. Okay, half m omega naught square a square e to the power minus 2 gamma t. Half m omega naught a square we have already seen. This is called E naught because it is a constant and it does not depend on time, or simply it is associated with simple harmonic oscillator. Or in other words, when the oscillator is free from other external force such as a damping and external applied force, then this is the energy. Okay, the energy will remain constant E naught, and e to the power minus 2 gamma t, and we can write e to the power minus t over tau. What is the tau? Tau is 1 over 2 gamma. What is the value of gamma? 2b over m. So tau will be m over b. So what we can see, the average energy of the damped harmonic oscillator when it performs under damped motion or oscillation will have energy this E naught, and the energy will decay exponential by this relation e to the power minus t over tau. What is the time scale of the decay? 1 over tau. Okay. So so that you need to calculate. Okay, so that's the total energy, average energy associated with the damped harmonic oscillator. Okay, and as I said, so this is a part of your assignment and you have to calculate it. Okay, so in summary, so we use the same approach we did for simple harmonic oscillator, and we found the solutions associated with damped harmonic oscillator, namely underdamped, overdamped, and critical damped. Okay, and we studied in great detail this solution by plotting them, and then we find their physical significances or what they actually represent. For example, the overdamped critical damped represents that the oscillator, if you pull it and release it, it will never move the other side of the mean position. That means it won't perform any oscillation, or they don't perform any oscillation. Whereas the underdamped, it performs oscillation. And we explain why they got named like that: underdamped, overdamped, and critical damped. And finally, we calculate the total energy. In fact, I asked you to calculate, and it is indeed a part of your assignment, which I am going to upload by today. Okay, so is it clear to everybody?
Yes. Yes, sir.
Yes, sir.
Yes, sir.
So any question or any doubt? Any doubt?
Sir, why we have to upload assignments after clearing them?
Okay, by the way, so I'm going to upload this lecture note as well as the recorded videos, maybe after in half an hour. So you can go through it. If you have doubt, you can go through video lecture, and you are free to discuss among yourself. And by the way, I'm going to upload assignment. All details will, all details, or all the detailed informations are given in the assignment. Okay.
Okay, sir. Thank you.
So that is all about
assignment where we have to submit the previous assignment.
No, the problem, I have given you in the last lecture, right?
Yes, sir. Yes, sir.
So that is also part of the original assignment. So as I said, all the instructions are given in great detail, and you have to follow them and you have to submit. Okay.
Yes, sir. Where we have to submit, I am asking.
So that, everything, as I said, everything, as given in grade. Once I share, you'll understand, right, what I mean. Okay.
Okay, sir. Thank
Okay.
you.
Where we have to write assignments, sir?
As I said, okay. So let me, see it, show you a typical assignment. For example, okay, here is a typical assignment. Let's say, okay, do you able to see?
Yes, sir.
Yes, sir.
Yes,
So,
sir.
is it visible, the instructions?
Yes,
Yes,
sir.
sir.
So like,
Yes, sir.
the mark 3, the deadline of assignment submission is this, blah, blah, blah. Okay. And then in addition to that, let me open this in a PDF file. Okay. So this is, some semiconductor period course. Okay. It is mentioned, right? Assignment solution soft copy must be submitted at Google Classroom. And then it is mandatory that the top of the first page of the assignment answer sheet must contain assignment number, branch name, student's ID, student's name, and the rest of the pages must contain ID at the top right corner. You should start answering questions from the first page which includes above items. Answer sheet will not be considered for evaluation if above items are found missing. And then you can use, soft copy. That means you can write in a paper, A4 size paper, and scan it and upload it as a PDF file. Okay. Got it?
Yes.
Yes, sir.
Yes
Yes,
or
sir.
no? Okay.
Yes, sir.
Yes, sir.
So this is a typical assignment. Okay. So all the instructions again. For example, duration 2 weeks. The date I post, I'll post the assignment. We'll get the 2 weeks time. Okay. And in addition to that, as I said, more instructions are given. Okay. So you have to upload. If you go to Google Classroom, for example, you can find assignment students have been uploaded. This is exam, this is assignment. So you can see, right? So students have been uploaded. Here assignment. Let me go through it. So all this notification will come. Okay. And you can see, right? Do you able to see?
Yes, sir. Yes,
Yes,
sir.
sir.
So once you upload,
Yes, sir.
so here.
Sir, we don't have to copy the questions right on the assignment sheet.
No, no need to write the question. Okay. So let me show you a typically assignment a student has done here. Okay. Okay. You can see, right? Assignment number, branch, ID, name, as I mentioned in the instructions. Okay. And then in answers, and you'll find these things. The second page, ID. First page, all details, and the rest of pages, only ID. You can see, right? The ID is given the student. Okay. Got it?
Yes, sir.
Yes, sir.
And you'll get some marks. Okay. A few, typical, numerical problems I'll solve during the lecture hour, but most of the problems you'll find in the assignment. Okay. And my advice is you should solve assignment parallel with the lectures. Okay. Then you'll get the, because you will study the theory, and if you do the numerical problems, then the concept will be much clearer. Okay. So, and in addition to that, some marks will be given for the assignment. For example, for this assignment, 3 marks, right? So 3 marks, it's a 5 marks. So if you submit and if the answers are, correct, then you'll get the 3 marks. If you don't submit, then you lose 3 marks. And in addition to that, you'll find some of the numerical problems, not exact problem, but some variant in your exam. Okay.
Okay,
Hello,
sir.
sir.
It is essential to solve all these assignments. You'll get the double benefited. In the sense, you'll get some mark if you submit the assignment, and in addition to that, you'll find some numerical problems in your exam. Is this clear?
Sir,
Yes.
when to submit last lecture's assignment?
No, as I said, that assignment, that simple problem, one problem you'll find in the assignment one that I'm going to release by today. Okay, and you have to submit that. You'll find this a part of the problem.
Okay, sir.
And the today problem, as I said, in average energy, you have to calculate. It is also part of the assignment one. Okay, and you'll find 20 to 30 numerical problems on the first chapter in first assignment. Okay, I think I should stop here, and I have clarified or answered whatever queries or questions you have. So if you have any further questions, you can ask me. Okay, so if no more questions, I think we should stop here, and tomorrow we'll meet. When is the lecture tomorrow? 11, right? Yes or no? Is it 11 o'clock? Do you able to hear me?
Yes, sir.
Hello?
11.
Okay, so do remember, whatever the schedule beginning time of your lecture, you add 5 minutes. We'll start lecture there. For example, today 2, we started 2:05, and then tomorrow 11, we'll start 11:05, because so you'll be on online mode class. Probably some faculty, they'll cross little bit time, and you have to again disconnect, join, and these things. Okay, so it will consume some time. So I'll give 5 minutes in between them. Is it clear?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Okay, so bye.
sir.
We'll meet tomorrow to discuss about force-damped harmonic oscillator. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Yes, sir.
Thank you, 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 sir.